the day that you're going to try to explain to me? So, all right, ladies and gentlemen. So, yesterday we started talking about gases, and we said there were 4 factors that can affect the gas. One is pressure. One is temperature. Volume. And amount of gas. For amount of gas, we use N. For volume, we use V. For temperature, we use T. And for pressure, we use P. Okay? Those are the 4 factors that can affect the gas. Okay? Today, we're going to be talking about converting between temperature and pressure scales. Okay? We're going to get through probably about up to slide number 22 today. And I got a demo for you that we're going to show you right here, right now. So what I have, ladies and gentlemen, is this is a vacuum plate. It has a hole in the center of it. It is connected to this pipe on the bottom and then these 2 valves. One of these valves is connected to our vacuum pump that we used yesterday that Joshua so eloquently demonstrated at the end of class yesterday. Thank you very much, gentlemen, for doing so. So when I turn on this vacuum pump, ladies and gentlemen, a vacuum pump will take and remove air from one area and put it out in another into the room. Now, until I shut this valve, all this is doing is just coming right through these 2 valves, but I'm going to shut this valve right now. So right now, happening inside this container is we are taking and we are removing some of the air from inside of here. Okay? So hopefully that's pretty good, ladies and gentlemen. I'll shut this valve so that I can then turn it off. Now, which of these 4 things has not changed right here, right now? I haven't done anything with temperature. We didn't heat anything up. We didn't cool anything down. Temperature cannot have changed. What else? This container is not changing its size, is it? So the volume is the same. Okay? So, explain to me how this happens. Okay, what is suction actually? What about it? I'm sorry, one more time, Morgan. Okay, so let's go back. What was being taken away from the container? Okay, so what is that changing? The amount of gas. We're literally taking the gas out of inside of this container, correct? That is lowering the amount of gas. The amount of gas is going down. Now, it has to change one other thing, because you cannot change one of these things without changing another. Well, there's only one thing left that we have not talked about. What is it? Pressure. So if we take the air out of this container, the gas out of this container, if this goes down, what happens to the pressure inside there? So by taking the gas away, the pressure is going to go up? Well, that's my question to you, because those are the only 2 options, right? Okay, let me state this. Yesterday we talked about pressure as being the amount of force applied over a certain area. Today we're going to talk about the pressure of a gas. Okay? Now, think about the gas particles in this room. They are incredibly what? Tell me something about the gas particles in this room.
Small.
They're incredibly what?
Small.
Small.
Fast.
Incredibly fast moving. Good. What else? How many of them are there? A lot. Okay? Now, if I take a bowling ball and throw it at you, Phoebe, are you going to try to get out of the way? Or are you going to try to catch it?
I'm trying to catch it.
You're going to try to catch it. 16-pound bowling ball thrown at you.
That would be my first reaction.
Okay. How about if I fired the bowling ball out of a cannon?
And then I'd move out of the way.
Okay, good. Why?
Because it's faster.
It's going to hurt,
And it's
right?
scarier.
Okay. What if I threw a feather at you as hard as I could?
I would laugh.
Why?
Why would you do
Why not?
it?
Would you get out of the way in fear for your life?
No,
Why not? It would be moving at the same speed as the bowling ball.
because it's lightweight.
Okay. So, if something doesn't have a lot of mass, let's use a science term, and it's thrown at you, it cannot have a lot of what kind of energy? Kinetic energy. If an object has a very tiny mass, I don't care how fast it's moving, it can't bring with it a lot of kinetic energy, correct? So what does that tell you about the gas particles in this room?
It can't hurt us.
They're probably not going to hurt us because their mass is so small. But also yesterday, we increased the pressure on the bed of nails by doing what? Okay? Increasing the mass doesn't affect force. We change the force, right? Okay. So the air particles in this room create pressure. Okay? They create pressure. But even if they're moving faster and they hit you, is that going to make a big difference? Maddie? No, it's not, because their mass is so light. So how do gases actually create pressure? Not by pushing with a lot of force, because they're so light they can't have a lot of force. Gases create pressure by how often they hit something. How often they hit something. Okay? So imagine anybody ever see the game Pong?
Yeah.
Describe it. Tell me about it.
Two little like blocks and the ball, and they hit the ball with one of them.
And when the ball hits one of the blocks, what does it do?
Bounces off.
Bounces off of it. Okay, imagine one gas particle blown up to the size of a ping pong ball. It goes in and hits that wall. What's going to happen to it?
Gonna bounce off that one.
It's going to bounce off that wall and do what?
Hit this wall.
Come and hit this wall. And then it's going to bounce back. And imagine it just bouncing back and forth all day long. That is how a gas creates pressure. Now, how can I make it hit the walls more often? What could I do?
Bring them closer together.
I could bring the walls closer together, right? It would spend less time traveling between them. It would hit the walls and it would hit them more often. That would increase pressure because it hits the walls more often. How else could I increase pressure? How else could I make ping pong balls hit the walls more often?
Increase the velocity.
What?
Increase the velocity.
I could increase the velocity. How do I increase the velocity of a gas?
Temperature. Heat up.
We heat it up. We change the temperature. So if the ping pong ball is moving faster, it's going to hit the walls more often, correct? What's another way I can make it hit the walls more often?
More.
I could put more ping pong balls in the room. If I put 3 ping pong balls in the room, all moving at the same speed, it's going to hit the walls 3 times as often, right? That is how gases create pressure. Okay, so there were gases on the inside of this container hitting against the glass wall. What have I done to the amount of gas inside there?
Decrease it.
So what does that mean for how often the particles are hitting the walls of the glass inside?
Not often. Not
It is going down, not as often. So what has happened to the pressure?
It decreased.
Good. So now why can I do this? Again, you use the term suction, right?
Yeah.
What causes suction? Same reason Josh and Josh had a hard time pulling apart the spheres yesterday. What causes suction?
Pressure.
What about it? What do we know about the pressure in this container?
There's a low pressure.
Low pressure. What do we know about the pressure all around it? In comparison,
There's more.
high pressure. We know the pressure inside is lower because we've taken some of the air out, right? We've taken some of the air out. There's less air inside here. There's low pressure inside here now. High pressure outside. What is the high pressure trying to do? Trying to get inside. It's trying to equalize the pressures. Pressures will always try to equalize. If there is an area of low pressure around, high pressure will try to equalize it. We'll try to raise that pressure up. The problem is right now the air has no way of what?
Getting in.
No way of getting in.
Nice. The air got it.
Why did it fall?
Because you allow air.
And what happened when we allowed air in?
The pressure.
The pressure went up. And eventually the pressures got to the point where they were equal. Equal. And when they're equal, now there's nothing pushing, trying to get in here. The pressure inside is equal to the pressure outside, which means all I got to do is lift this. Who lifted the 1,500-pound book yesterday? What'd you have helping you?
Oh, the pressure.
1,500 pounds of air pushing down on the book, but also
Air up.
1,500 pounds of air pushing up. All you have to do is hold up the book. Same thing here. When the pressure inside and outside this glass jar are equal, all I got to do is lift the glass jar. When the pressure inside and outside are not equal, high pressure tries to get into low. Okay? High pressure tries to get into low. Okay? Questions? Doing pretty good.
It's just like doing something.
Most, not a big fan. We won't discuss why.
Is it okay?
What happened to the balloon?
Bigger.
It expanded.
It expanded. It got bigger. What changed?
Wow.
What?
Wow.
Volume. Why?
Because
Because
the
the
pressure
pressure
lower.
decreased.
What?
The pressure lower than the container.
Why did the pressure lower in the container?
Because we took gas out.
Because we took gas out. This is an interaction of all of those things, correct? Taking gas out causes the pressure to lower. The balloon inside starts getting bigger. Why?
Because it's trying to fill in the gas that we took out.
Why?
The pressure won't go inside.
Okay, now remember, originally, right now, what could we say about the pressure inside this balloon and outside this balloon? Why?
Because there's no force acting.
Well, if the pressure inside the balloon was higher than the pressure outside, what would it be trying to do?
Well,
Trying to equal out, right? Which would mean it would be trying to take up
Space.
more space, right? What if the pressure outside were greater than the pressure inside? It would deflate. The balloon would get smaller because the pressure outside would be pushing in on it. So right now the two pressures are what again? Equal. What do we know about the two pressures inside the container and inside the balloon right now? They're equal. They're equal. But to be equal, what had to happen to the volume of the balloon? It had to expand and get bigger. When have you possibly experienced this, ladies and gentlemen? No. That's a good thought. But here's the problem with breathing. Right now, the air in the balloon cannot what? Can't escape, right? When we breathe, we're actually letting air out of our body and taking air in. Okay, now it does change the volume of our lungs. They expand and they go down as we breathe, right? But again, it's not like a closed system like this. Okay? But when will you sometimes experience something like this, ladies and gentlemen? When you fly. What happens to some people when they fly? Especially when taking off.
Their ears go up
Why do your ears pop?
Equalize the
because of the
pressure.
pressure.
What?
To equalize the pressure in your body with the pressure around you.
Yes. When you get in a plane and you start going up, up, up into the air, what's there less of on top of you?
Oxygen and pressure.
Well, just let's say air. So if there's less air on top of you, air pressure is actually going which way? Down. Where is a terrible place for an athlete to have to play?
Like really high up.
Like really high up. What city? No, not Canada. Not high up meaning north.
Denver.
Why?
Because they're higher altitude. From
What is
somewhere.
Denver known as? The what city? Mile High City. They are a mile above sea level. In Green Bay, we are 600 feet above it. Okay? So imagine on top of you right now a stack of books going all the way up until the atmosphere ends and we get into outer space. A lot of books, right? Now, if we go up 5,000 more feet higher, what happens to the number of books on your head?
Decreases.
What?
It would decrease.
It'll decrease, meaning there's less air pressure on you. Athletes hate playing in Denver because less air pressure means when you are competing and you take in a breath of air, you're not getting as much air because it's lower pressure. And it takes a while to get used to. Now, athletes who train in Denver, not a problem. Where do a lot of our Olympic athletes train at? In places with high altitude. Why? Because it's easier for the Denver athletes to come down and play at sea level than it is for a sea level athlete to go and play at Denver. So a lot of training facilities, not all, but a lot of them, are in areas where it's a higher altitude. You train under more extreme conditions. Okay? So, okay, this is what happens with the air in your ears. You're right, it pops. Why? The air inside your ears starts expanding, getting bigger and bigger and bigger. And eventually it has to go somewhere. Now it has two choices. It pops out of your ear or it bursts your eardrum. Those are the two choices. Luckily, normally it goes out of your ear. What do they suggest you do if you have trouble with your ears when you fly?
Keep going.
Why? Your jaw connects right back here, right below where your ear is. And normally the motion of chewing and moving your jaw causes your ear to just move a little bit slightly, giving the air an easier chance to escape. Okay? Giving the air an easier chance to escape. Now, we take and we put the pressure back in here. What happens to the balloon? Goes back to its normal size. When have you experienced that?
When landing.
What?
When landing.
True. When landing. When else though?
When going underwater.
When you go underwater.
Yeah.
If you've ever gone to a deeper pool and dove down to the bottom of it, what does it feel like is happening in your head?
Your ears.
Your ears hurt. Why?
There's a lot of pressure on top of you.
Because now, instead of your ears, the air inside there expanding and wanting to get out, now the air inside there is contracting and pressure is trying to get in. Now you dive down into the bottom of a 12-foot pool, you come back up, everything goes back to normal. What if you're scuba diving?
You have to slowly come back up. So air isn't in your.
Right, but even as you go down, They have to do what is called equalizing pressure. How many of you have ever gone to sneeze and you accidentally plugged your nose right before you sneezed? You know what I mean? You do one of these and you pinch too hard. Feels like your ears are going to go flying out of your head, doesn't it? Divers have to do that when they go down deep into depths. They plug their nose, they blow into their nose, it puts extra air into their ear canal. It equalizes the pressure. Okay? It equalizes the pressure. Okay? Because now you not only have the pressure of air trying to push in, you have the pressure of this water also trying to push in on you. Okay? The last thing they do when they certify you to scuba dive, the last thing they do is they take you down 60 feet. They make you drop your tank, they make you drop your weight belt, and you come to the surface on one breath. The worst thing you could do is hold your breath while you're coming to the surface. Because what happens as you come to the surface to the gases inside you? They expand. Why is that a bad thing if you hold your breath? Because your lungs can only expand so much. So you can literally go from 60 feet underwater to the surface on one breath, exhaling the whole time because the gases inside your body are starting to expand. And all you do is exhale all the way up. And if you don't, you're in trouble. Okay? Because of all the interactions of pressure and volume and temperature on gases. Okay? All of those things. All right. So, again, here we go. What's the balloon doing? Good. Why are you panicking? You feel like it's going to pop. That balloon, you don't... Oh my God! It popped, ladies and gentlemen. Did you all hear that?
Really scared.
Why didn't you hear it?
Because boys can't.
Thank you. Sound cannot travel without air. We didn't actually hear the balloon pop. What did you hear? When it hit against the glass, because then it could finally create a sound wave that could travel to your ears. There wasn't any air inside there for a sound wave to create. Okay? Questions? Good. All right, open up your EISN, ladies and gentlemen. Let's get to what we got to get to today. Chemists like me. Gosh, there's a phrase that scares the heck out of me.
I'm not a chemist.
By the way, this is why they tell you never to fly if you have a really bad what? If you have a really bad head cold. Because think about it. If your sinuses are plugged up, you're going to have a lot harder time equalizing the pressure inside and outside. And you can actually blow out your eardrums from the pressure if you cannot equalize the pressure. Okay? Can't equalize the pressure, you're in trouble, ladies and gentlemen. All right. So, what is KMT? Refresh me. What does kinetic molecular theory say? All matter is created equally by one God, indivisible, with liberty and justice for all. No. All matter is made up of we already did that. We're not going back there. All matter is made up of tiny particles, and those particles are constantly moving. Okay? So in terms of pressure, ladies and gentlemen, in terms of pressure for KMT, it is not the amount of force over an area. In terms of pressure, it is the constant bombardment of particles on the walls of a container. The constant bombardment of particles on the walls of a container. That is what causes pressure. the gas particles in this room that are hitting the walls, that are hitting your forehead, that are hitting your chest, that are hitting your back, that are hitting any surface they can get to, ladies and gentlemen, are causing pressure on you. How much? About 15 pounds per square inch, the same as that bar that I showed you. Although it's probably a little bit lower today because we are a little bit above sea level. And it changes day to day depending on the weather. Okay? Now, if you want to increase pressure, well, we could change the area. Right? We showed you that yesterday. Go to a smaller area, increases the pressure, correct? What can happen with force that can change pressure? More force. The problem is we can't do those things with gases. They're already tiny particles. You can't change their area, and they don't hit with very much force. So according to this definition, what is the only way to increase pressure? No.
When the particles hit the wall.
They're already hitting the wall. You're close.
More often.
More often. The only way to increase pressure is make the particles hit the walls of the container more often. Make them hit the walls of the container more often. How? By changing one of these three things. That will cause them to hit the walls of the container more often. So how do you decrease pressure?
Not as often.
Make the particles hit the walls of the container less often. That is the way we are forced to look at pressure because we cannot talk about a gas exerting a force over an area. It just doesn't work. So we look at it in terms of kinetic molecular theory. Pressure is how often particles hit the walls of a container. If you can make them hit more often, your pressure will go up. If you can make them hit less often, your pressure will go down. How do you do that? You change one of these three things, ladies and gentlemen. Questions? Good. Anyone need more time before I move on? Irving, you got it? Okay. Now, before we go too far, couple things we need to understand about gases. There are some assumptions we make about gases that may or may not be true, but we make them anyway. I will not test you on this. I will not quiz you on this, but I want to explain this to you. Number one, gas particles do not attract or repel each other. Is this true? Do gas particles attract or repel each other? Well, if gas particles ever go to a liquid state, what holds liquids together? Think back to Unit 2. What holds a liquid together? What holds a solid together, ladies and gentlemen? Starts with forces. Forces of attraction. So do gas particles, are they attracted to each other? Yeah. Otherwise they would never make a liquid. They would never make a solid. But what do we know about gas particles? They move fast. And they what? Far away. Is this magnet attracted to the metal frame here? Still attracted? What? Is it still attracted though?
Oh yeah.
Oh. Yes. Is it able to go flying toward the metal? No, why? Because we're too far away. So even though there is a force of attraction, if we move the objects far away from each other, do they attract each other? No. Because they're far away, they would not attract each other. The other thing is, all right, is this magnet attracted to the board?
You did it this time.
Yes, I did it this time. Yeah, I'm getting better at this. But if we throw this hard enough at the board, it bounces off. Why? The force from when they hit each other, wanting to bounce off each other, is greater than the force trying to what? Hold them together. And we know that gas particles are already moving what? Moving fast. So because they're moving fast, even if they do manage to hit each other, They will bounce off each other. So we can assume that gas particles do not attract or repel each other. That's the reason. Number 2, gas particles are in constant random motion, traveling in straight lines until contacting something. So there is a gas particle moving right towards Angel's head. It doesn't go right around it. No. It hits him dead center in the forehead and then does what? Bounces off in another straight line. Now, how do we know that all the particles in this room are moving in constant random motion? What would happen if all the gas particles in this room were moving in the same direction? What?
You would see it.
How?
I don't know.
Because your hair would be moving in that same direction. As all the gas particles are moving across the room this way, your hair would be blowing this way. Then when they hit the wall and bounce back, your hair would go the other way. That doesn't happen. Why? Because the gas particles are going in all different directions. Okay? They're going in all different directions. Third one. Gas particle kinetic energy is directly proportional to their temperature. Meaning if temperature goes up, kinetic energy goes up. Meaning if temperature goes down, kinetic energy goes down. Gas particles have perfectly elastic collisions. What is that?
They bounce off each other. They come on.
Not only that they bounce off each other, but when they bounce off each other, they don't slow down. Two objects hit each other in the real world and bounce off, they slow down. They lose energy. How do we know gas particles don't do that? Okay, true. But what would indicate that gas particles are slowing down every time they hit something? What would happen to the gas particles if they slowed down? What?
Liquid.
They would eventually slow down enough to where they would become a liquid. You and I would be trying to suck the liquid oxygen off the ground because there'd be none in the air. We'd all be dying. But no, they stay moving at perfectly elastic collisions. They don't slow down. Okay? Last, gas particles have no volume. Is that true?
Unless they're in a container.
Even in a container.
They take up
Okay, but the particles themselves, the little pieces that make up the gas, do they have a volume? Do oxygen molecules have a volume? You bet. Otherwise, they can't be matter. Matter has to have mass and take up space, right? But what do we know about the size of an oxygen molecule? Teeny. What do we know about the size of the space that the oxygen molecules are occupying here? Really big. So even though they are very tiny, compared to the amount of space they normally occupy, it's like they occupy none of the space. Okay? They occupy none of the space. Okay? Those are the assumptions we need to make for gases, ladies and gentlemen. Those are the assumptions.
Who figured this out?
Who figured this out? Some people who were way smarter than me, and no, it wasn't Mr. Arts. Okay. So air pressure, ladies and gentlemen, we talked about this. Air pressure is the pressure that air exerts on us every minute of every day. Air pressure works in all directions because the particles are moving randomly all over the place at any surface it can get to. Okay? Pressure is reported on the weather as inches of mercury or millimeters of mercury. Even right now while you're sitting, can air particles get under your butt on this chair?
Probably.
You bet, because you know what would happen if they didn't?
No.
You'd never be able to stand up.
Oh.
You'd have 15 pounds of pressure on every square inch of your body, except which is in contact with the chair. Which means when you go to stand up, you would have to overcome all of the pressure from your legs and your torso to be able to stand. 15 pounds per square inch. 1,500 pounds in the book. How many books are there between your legs and your chest when you're sitting in a chair? Think about that. You'd never be able to get up. Okay? Never. Okay? Air pressure is normally about 14.7 psi. That's where we get the 15 from. That's why I've been getting that number for you. Okay? All right. So let's talk about temperature, STP, and conversions. All right. First of all, temperature has to always be in kelvins. You cannot do a problem if temperature is not in Kelvin. Now, some problems will not involve temperature. If it's not part of the gas law, you don't have to worry about it. But if it is, we have to put it into Kelvin. Now, easy to get into Kelvin, though, ladies and gentlemen. But Kelvin is an absolute scale. What does that mean?
No negative.
No negative numbers. Absolute means no negative numbers. 3 scientists created the temperature scales we have: Celsius, Fahrenheit, and Kelvin. Celsius and Fahrenheit did it by taking a glass-filled tube with a liquid inside it and putting it into ice water. They marked the tube. Celsius picked 0, Fahrenheit picked 32 degrees. They said that's the freezing point. They then put that same tube filled with that liquid into boiling water. The liquid inside there expanded, rose up. Celsius made a mark, said 100. Fahrenheit made a mark, said 212. I don't know what Fahrenheit had against easy numbers, but he used 212 and he used 32. I don't know. Maybe it was his favorite days of the month or so. I don't know. Okay? Now, Kelvin said, if temperature is kinetic energy, what is the lowest temperature you can have? Which means how much energy do you have? 0. He wasn't worried about where water boiled. He wasn't worried about where water froze. He said, all right, we're going to go to the point where matter stops moving. Matter stops moving. You're going to prove it in here as well, what that temperature is. Okay? So no negative numbers in Kelvin. Why? If we have a negative number for temperature, we would have to be able to have a negative pressure, negative volume, or negative amount of gas. And we can't do any of those. K is the symbol, no degree sign, ladies and gentlemen. And if I were you, I would write this formula somewhere on your periodic table because you are going to be asked to do it on your quiz on Thursday. I would probably put both of these on there because you may want to go from Kelvin to Celsius. You may want to go from Celsius to Kelvin.
Mr. Brand.
Yes.
On the test, you did put the definition of chemistry.
You're right, I didn't.
Are you gonna still do that?
It'll come back at some point in time. Who knows? You guys are so advanced, you got so good at it, I thought, why should I put it on the test again? Although I did give it to my other chemistry A class this morning, and ooh, some people are not good at writing a definition down, I can tell you that.
Wait, what is your word? And she has it different. And
Science is the study of matter, its structure, its composition, and changes as it goes.
yeah, that's what
You mean SMS? Is that not?
Which two? Which two?
12 and 13.
You think I memorized all the questions I meant?
Answer.
Prancer is the reindeer, and white.
See,
Tungsten, hydrogen, iodine, and tellurium. White.
I just guessed on this
well,
one.
I
got it right.
Color.
Which one?
Oh, but what's Santa's favorite song?
What? Looking at the list, what are you going to do? Put carbonate down? Coco? Actually, that might work. Dang it, that would have been a great question. What do people like to drink during winter? Coco?
I just guessed on that.
You guys are giving me problems to use for next trimester. Good job. I got 2 more chemistry B classes next trimester.
And Alexa.
No, John, make sure you don't.
Okay,
And Lucy.
Sorry.
so ladies and gentlemen, if you are going to go into Kelvin, you take your temperature in degrees Celsius and you add 273 to it. Now, can you have a negative temperature in degrees Celsius?
Yes. Yeah.
What's the coldest temperature you can have in degrees Celsius?
Negative 273.
Negative 273. Because then when you add 273 to it, what do we get? 0. You can have a negative temperature in Celsius. You cannot have one in Kelvin. So there is no minus 274 degrees Celsius. You cannot get that cold. Okay? Now, to go from Kelvin into Celsius, we're going to take our temperature in Kelvin and we are going to subtract 273. But please remember, this number can come out to be a negative. Nothing wrong with that. That number can come out to be a negative. Questions? So 50 degrees Celsius, what is it in Kelvin? You're reaching for a calculator. To add 50 to 273.
323.
What?
323.
323. You can reach for your calculators. It's okay. It's okay. What if it was 85 degrees Celsius? 358 Kelvin. Notice no degree sign. The number in K for Kelvin. What if it were negative 50? 223 Kelvin. Okay? 223 Kelvin. What if it were 425 Kelvin? Minus 273, 152. Very good, Josie. 152 degrees Celsius. What if you were 185 Kelvin? Negative 88 degrees Celsius. Negative 88 degrees Celsius. Anybody need help making the degree sign? I'm a big fan of cutting and pasting.
It's already there.
Okay. The answers?
No, the
Degree Celsius sign?
Yeah.
Okay. What if you have 1245 Kelvin?
972.
972 degrees Celsius. Very good. Questions? So 4 problems like this on the test on the quiz should be easy peasy, correct?
Could be.
Okay, good. That's all there is to converting temperature in Kelvin.
That's easy.
Now, here's what I'm going to tell you right now, ladies and gentlemen. When we give you the unit test, 3 or however many weeks from now, there will be at least 3 people in here who do the entire test, do everything absolutely perfect, and forget to convert to Kelvin and get every problem with Kelvin wrong. Every single problem. So if you are working gas laws, problems, and temperatures involved, you have to put it into Kelvin. Even if both temperatures would be positive values, it goes from 20 degrees Celsius to 40 degrees Celsius. You still have to put it into Kelvin. Okay? You still have to put it into Kelvin. And here's the reason for that. Give me a temperature, somebody. In Celsius, please. 19. Okay. So if it goes from 19 to 38 degrees Celsius, what happened to our temperature? How much? What did it do? Okay, what's another way of saying that? It doubled. Right? Then if we go from 38 to 76 degrees Celsius, what happened? It doubled, or this went up how many times? 4 times, right? Okay. Now, give me 19 degrees Celsius in Kelvin, please.
Negative 252.
Eh,
No, wrong. Is it 292?
292 Kelvin. Oops. 292 Kelvin, correct? All right, give me 38 degrees Celsius in Kelvin. Give me 76 degrees Celsius in Kelvin. This from 19 degrees Celsius to 76 is a 4 times increase, correct? Went up 4 times. 292 to 349, is that a 4 times increase? No. No. If the temperature were to double around us tomorrow, the pressure of the gases around us would double as well. We would get crushed under the pressure of the atmosphere. But going from 19 degrees room temperature to 76, close to boiling, never going to get that hot on our planet, would be a 4 times temperature increase, correct? It's not a 4 times increase in Kelvin. Okay? So understand, if we talk about the relationships here, think about this. If you went from 1 degree Celsius to 2 degrees Celsius to 4 degrees Celsius to 8 degrees Celsius to 16 degrees Celsius, that's a 2, 4, 8, 16 times increase in pressure. From 1 to 16 degrees Celsius. You and I would die under that pressure. Okay? But in Kelvin, this is 274, 275, 277, 281, 289. That is not that big a change, is it? Okay? That is why we have to use Kelvin, ladies and gentlemen. Have to. No ifs, no ands, no buts. Okay. So we talked about STP. We already told you about STP in the last unit. Here's what it is. STP is a set of conditions we can compare to. STP is a set of conditions we can compare to. STP is 0 degrees Celsius or 273 Kelvin. That is the only temperature that STP is ever at. 0 degrees Celsius or 273. And it can be any standard pressure. Now, these are the 4 most common units, ladies and gentlemen. 760 millimeters of mercury. 760 millimeters. So, if you had a column of mercury in a tube, the pressure of the room would cause it to rise up that much above the table. 760 millimeters. It's literally how they measure the pressure. Air pushes down on it, the mercury goes up a tube, boom, we get the pressure. 760 millimeters of mercury. It's also 101.3 kPa. 101.3 kPa. Now, this 101.3 kPa, ladies and gentlemen, is 101,300 pascals. Now, to give you an idea of what a pascal is, we go back to our definition from yesterday. The amount of force applied over a certain area. If you were to take 1 Newton of force and apply it over 1 square meter, that's 1 pascal. That's what 1 pascal is. 1 Newton over 1 square meter. Now, look down at the floor. 3 of the floor tiles by 3 floor tiles is a square yard. That is just slightly smaller than a square meter. Okay? So that's how much space. Now take a medium-sized apple and put it on those 9 squares. That's how much pressure a pascal is. Meaning what? An apple sitting on an area that big, is it going to create a lot of pressure? Pascal is a very small amount. That's why we use kilopascals. Okay? Kilopascals. Okay? 14.7 psi and 1.00 atmosphere. 1.00 atmosphere is the pressure of the air above us when we are at sea level. That's 1 atmosphere. That's where that comes from. Now, 4 quarters, 10 dimes, 20 nickels, 100 pennies. All of those are what to each other? Equal. All of these pressures are equal to each other, ladies and gentlemen. All of them are the exact same amount of pressure. Different unit, different number, exact same amount. Which means, ladies and gentlemen, we can use these to convert from any unit of pressure to any other. Any unit of pressure to any other. So if we want to convert from 3.11 atmospheres into millimeters of mercury, we are going to take 3.11. ATMs. And we are going to make a conversion factor. What goes on the bottom of this conversion factor, ladies and gentlemen? Why? Only way to cancel out ATMs. What goes on the top?
760 something. I don't know if I have mercury.
MMHG. Now, here's what I will tell you, ladies and gentlemen. Do you remember how in most of our conversions there is a 1 in them? 1 on the top or 1 on the bottom? You may not get that here. You may end up with 760 over 14.7, 760 over 101.3, 101.3 over 760, 14.7 over 101.3. So you may have to multiply by a number and divide by a number in the same conversion factor. So if we take 3.11 times 760 divided by 1, what do we get? Come on, put those fancy calculators I let you use to work.
You want it rounded?
I want it in how many sig figs? 3. Okay, Phoebe, you got to be a little louder. I hear you saying numbers, but I don't know what they are.
236.
0.
Oh.
MMHG.
0.0.
Oh, wait.
I don't want naked numbers running around my room. Now, let's start, Phoebe, with the 236. I agree those were the 3 sig figs. But if we don't put the 0 in, what have we done to the number? Change the value of it. So now Stephen added the 0. Perfect. Caden added the unit. Perfect. Don't put 0.0. Why?
Oh, the 0.
The zeros would count. They would become significant. You would have 5 sig figs. Questions? All right. 85.0 kPa. All right. If we're going to go into PSI, what has to go where here, ladies and gentlemen?
101.3 kPa goes on the top.
What goes on the top?
14.7 PSI.
All right. So here's one, ladies and gentlemen, where you will not have a 1. Multiply by the number on top, divide by the number on the bottom. So, how many sig figs are we ending up with? 3. 12.3 PSI. Questions? Okay. Here's what I will tell you, ladies and gentlemen. I will, on a test, give you these.
Yeah.
Okay? I don't you by the end of this unit, you should have them memorized. But I will give these to you on a test. But you need to know how to use them. 12.3 PSI. How do I get to ATMs, ladies and gentlemen? 1 ATM on top. Bottom?
14.7.
How many sig figs? ATM is our unit. What do we got? 837?
Yeah.
Good. Good. All right. Hang on, I want to check something, ladies and gentlemen. What slide are we on?
21.
21? We were only trying to get to 22 today. How are we already on 21? You guys are that good, I will admit. And since you're that good, ladies and gentlemen, complete slide 22.
Bruh. I'm just kidding.
Let's go. Get it done.
I'm so excited.
If you need scratch paper to do what we were just doing, which is setting up your conversions, I happen to have some right here, ladies and gentlemen. You are welcome to come up and get some. Eric will hand you some if you ask him nicely.
Eric.
Oh. Oh, man.
No,
Even
you
ask me
can't. You
nicely.
can't come up here and borrow the one that's sitting up here waiting to go for you. He asked, not you. By the way, ladies and gentlemen, this is all of the stuff that will basically be on your quiz on Thursday. You need to be able to convert in the metric system. You need to be able to convert temperatures and pressures. Stephen, you can't reason with him. Just go to work. Hey, this isn't French class. Knock it off. No, it's not Spanish class either. Do you not know what class this is, Christopher? Yay.
Oh, wait, I think I get that. Like,
Wait, Mr. President.
this
what we're doing.
What do you want?
Yeah,
Go to the next slide.
Yes.
So on this slide, convert 81.5 millimeters of mercury into PSI, then ATM, then KPA. Is it 815?
Yeah.
Sorry, I misread
Hold
it.
on, let me
You're
cook.
815. Thank you.
I was cooking. And I'm like, wait. Like, I cooked this
I
gas.
know.
Oh, yes, cooked this gas. You put gas. Yeah, and then HG.
Alright, so you put 815 times and put a line.
Obviously, pero que va abajo.
Then you
Is it not
put
church?
FMD 760 button and you put PSI.
Thank you.
That's it.
I'm always scared to use this like bits of
Do
below.
the same thing 3, 4, 5, 6, 7, 8. 13 times.
Like I was good.
13 times?
Yeah.
Yeah.
So I don't know how.
¿Quién dice pendejo?
I literally would cook everyone in my class.
Okay, ¿y luego? Bueno, tenemos que comprar algo, ¿vale?
Okay, so I cooked.
I think what this is going to she's probably like recently.
What do you put for SAT? You give me the answer to the SAT.
See, I got, well, he did the rounding one. So you choose. So I don't know if I would have to go from that number to 18 or I'm gonna try it.
Well, you should put your answer in 3 sig figs.
The second one.
Quit kneeing up to him or whatever and sit in your seat.
So, 26 minutes.
Is it too much?
So let's say it's calculated as a converter from Celsius to Kelvin.
Bingo.
Probably does. Probably does.
So I'm cooking with gas.
I don't care.
I love cooking with gas.
Are you alive?
You look like the
You sure? Check.
1.0. 1.0.
I'm not fucking equipment for Z's up. Z's up.
Oh, he's right. I was right. All he did was
The third one.
okay.
I was a question. Chips?
I equaled it. Yeah.
Oh my god. I'm singing around.
Oh wait, no, yeah, I did it wrong.
Bro, I was so confused.
Yeah.
You are so confused.
Cause like,
Yes.
it's on enough study.
Well, if you're trying to go from MMHG to PSI, yes, you are. Yes.
Oh my god, yes.
I don't know.
Oh my god,
Lost my Mandalorian. But I
Who did a
actually
little
did.
mistake?
it's a 6 right here.
So 8.
Yes.
Oh my god.
I'm just here.
Why?
It's 'cause, like,
use
It was confusing because Angle got it wrong, right? And like, I thought he was right. Yeah.
Was that your answer when you went into ATM?
No, I was just looking.
Okay, so you've got to use the standard conditions there. That's why your numbers were
Yes.
off.
Later.
Now, when you convert it into ATMs, you could then convert that ATMs into the next one or the next one, however you want to do it. It doesn't matter. Or you can go back to that original one that just changed the factor on the bottom each time. It doesn't matter.
Don't even say anything because you thought it was.
How many sig figs are in that number?
Well, I did it.
So all of your answers should have 3
I'm
sig
so
figs.
smart.
Okay? So when you're doing sig figs, all of these numbers have how many sig figs? So every number that you write down should have 3 sig
From
figs.
this number to this.
Okay?
I think
So that's the way. That's the nice part about multiplication and division. When you know how many sig figs are in your original number, that's how many you put in your final answer.
No, I know.
Okay?
Mr. Brad,
Josie,
can I?
Hey, guess what's another thing?
Yeah, you
I don't
know.
know. You round up for this one to make it
What?
3,000.
Oh yeah.
Or,
Well, look,
2,000. Is that
no,
what you round that?
two, like, a 9.
Okay, where's the third sig fig in
Yeah,
that?
just the 2-1.
What?
Still 224.
Okay, but now remember, you need to do what with those other numbers that are before, that are to the left hand of the decimal?
Yes, I.
810.
To what?
Yeah,
If you've got a number that is like 2,375, and you are trying to round this into 3 sig figs, this is the third sig fig. You're now rounding into tens place, which means this becomes 238, and for this place, we have to put a 0 in there.
Yes.
Okay?
Okay, that's
So again,
I'm
those are your 3 sig figs. Rounding to the tens place, 0 in there without a decimal because then the 0 is not significant.
You're just asking me what you're doing. Just look at my face.
Over.
That's what I was supposed to do yesterday.
So that might be.
What did we have today?
I wouldn't go.
Who told you that?
Me.
Me.
Wait, well, I saw on the agenda that we're only going from side 17 to
We could keep going.
Okay. Keep going then.
Oh, no, that's right. I got it right. Oh, I was about to say.
Angle's confused.
Angles.
He can't tell what angle it is. You just
My phone translated it to
What?
translated it to bagel.
Whoa,
bagel.
that doesn't sound like alcohol. I
Sounds
swear,
better than
I was actually part of the cast.
What are you doing?
I just been held back on my words.
She didn't.
Alright, what do you get?
Oh,
I was looking.
Bro, hurry up.
okay.
I'm done.
It's your fault. You just do the math.
Right here.
Really? Really? That's all you got to say? That's it?
What are your bogeys there?
Hey, you guys are having a contest on who's more bogus.